Okay, this says a total charge Q is distributed uniformly along a thin straight rod of length L. What is the electric field at P1 at P2? Oh. Alright, so we want to find the electric field at that location, distance a by 2 away, and P2. Alright, so let's do P1 first. Alright, so the problem is symmetric. What we'll do is, so let's say, so this is 0, this is L by 2, this is minus L by 2. We'll find the electric field due to this piece. This piece is, let's say, distance x. This piece we'll call dq. This piece has an electric field like that. This piece has an electric field like that. You see the x component of the two electric field will cancel and only the y components add up. Everybody understand that? Okay. So let's call this dq. So here's our x, y axis. This distance r is, this is a by 2, and r square is x square plus a by 2 squared. So dF, the magnitude of the force, is k dq, no, not the dE. This is dE. The electric field is kq divided by r square. dEy is k dq r square, and dy is, let's say, this angle theta is cosine theta, and cosine theta is, that angle is theta. Cosine theta is a by 2 by r. So the y component of the electric field due to this guy is k a by 2 dq by r cubed. dq by r cubed x square plus a by 2. Oh, this is ugly. 3/2. Okay, what did we find? What is this expression? This is the y component of this field due to this charge at location x from the center. Okay, and all we have to do is, this is the y component, and we will just sum all of that for all these little pieces. Okay, so here's the integral. Okay, so the net electric field, which is just the y component, well, okay, Ey is the integral dEy. And it's this expression. So Ka by 2 dq x square plus a square by 4 to the power 3/2. Okay. Now dq is dq is okay, so a total charge of q. Here's q. So dq, the charge on this piece is, let's say the length of this thing is dx, and the length, so dq is q divided by L dx. The length of that piece is dx, the total length is L, so that's the fractional length, and fractional length times the total charge gives you the charge on that little piece. Okay. So EY equal to, and I will pull out the Ka to the outside, Ka by 2, dq is ql dx, x squared plus a squared by 4 to the power 3 half. That's the integral. And what are the limits for x for the integration? What are the limits? X goes from minus L by 2 to plus L by 2. Okay. So let me clean this up. We get an L out there. So K A Q Okay, so that's the integral. All right, so let's look up this integral. Okay, can you guys look up the integral? What is 2, 3, 2x? Can you Google an integral table? Do you have a table? Okay, so it's x over a by 2 x squared plus a constant, and we're going to apply, so that's the integral. Something is bothering me. We'll see in a second. Okay, so that's the integral, and we have to apply the limit. So the constant cancels when you apply the two limits. So k a q by 2l. That's number 29 in here, and we'll see. Okay, so at the top limit L by 2. Oh, by the way, so this A by 2 cancels with that A by 2. Okay. KQ by L. L by 2 minus a minus a plus L by 2. Okay. All right, so that's what it works out to. And so that's L KQ by L. This is twice that, so L divided by L squared by 4 plus A squared by 4 to the power half. The L cancels, KQ. Whoa, something went wrong. Okay. All right, where did I make a mistake? Okay. Okay, so here's what's bothering me. This length is canceling with that length. The electric field needs to have L's length square at the bottom, and there's a square, and half of that is length. So we're missing a length, dimension of length. This integral doesn't seem to be right if you do the derivative of that. Mm. All right, that it looks like that table is not right. So yeah. I mean that integral, this doesn't look right. This doesn't look right to me. Because if you take the derivative, I'm sorry?
Yeah, you used the wrong one. I guess it would still work. So then it would.
Yeah, that would work. Okay.
Yeah, so then you can still have.
Okay, yeah, there's the missing. So this is, oh, so this is, okay. K A by, this is A squared by 4. All right, now we are getting someplace. So one of them cancels, and so this is A by 2 is left over. A by 2. And so, okay, now 2KQ over A and 1 over L squared by 4 plus A squared by 4 to the power half. Okay? And so we'll pull the 4 out, and so that gets to 4KQ divided by A, 1 over L squared plus A squared to the power half. That 4 is still bothering me. Okay, so here's how you look at it. Oh yeah, no, the 4 is fine. Okay, so how do we know if we did it right? Okay, what we'll do is we'll take the limit L going to 0. Then this becomes a point charge, and the field from a point charge is just kq divided by this distance squared. And you see in the limit, so this has the right limit. Add a page below. So yeah, we did it right. So EY is 4 kq divided by a 1 over L square plus a square to the power half. In the limit EY, limit L going to 0 is 4 kq by a 1 over a. This becomes L goes to 0, that's that, and that is equal to kq a by 2 squared, which is what you would expect. Okay, so it has the right limit. So that integral was correct, except that I'd missed the a square part. Okay, so that's just this part. We found the electric field there. Now we have to find the electric field here. All right, so that's setting up another integral. And what time is it? 1:50. What I'll do is let's do it right now. We'll start the lab in half an hour or so. Okay. Are you guys cool with that? Everybody is not, but let's finish it. Okay. I'll do it fast. Okay, part B. Okay, now so we are setting up, we are finding the electric field at a distance A. Okay, again, we'll find the electric field due to a charge dq. We'll call this so we'll okay, let me set it up like this. So we'll call this 0, this x, and this is L. Okay, so dE is equal to k dq divided by this distance square. This distance is that was x, L plus a minus x. Okay, this distance is, this entire distance is L plus a minus x. L plus a is this entire distance minus x. Okay, so this is equal to L plus a minus x squared. And dq is, you saw, is q divided by L dx. That's dE. Okay, so the total electric field is dE, which is k q by L dx, L plus a minus x squared. And x goes from 0 to L. Okay. So that's the integral. So I'll pull out the constants. The electric field is kq by L, 0 to L dx, L plus a minus x squared dx. Okay, and now this integral is 0, is easy to do because there's no x squared there. This is easy. Okay, so kq by L, and the integral is L plus a minus x. That's the integral. Derivative of that would be minus 2, minus 1. Yeah, minus 1. Yep, so this is the integral, 0 to L. Okay, so the second integral is easy, kq L, and so 1 over a is the top one, minus 0 is 1 over L plus a. And a times L plus a minus a L, kq over a times L plus a. And again, so there is the electric field, and again this has the right limit. Okay, so electric field at this point at a distance a, this is L, E limit L going to 0. If you make this a point charge, this distance kq a by L plus a goes to kq divided by a squared. If you make this a point charge, if you squeeze this into a point charge centered there, the electric field goes to kq by a squared, the same as a point charge. Okay, so again that limit is correct. All right, so for this one I will solve the problem and post it online later. Okay, so we'll stop.